Hello, everyone. Let's now begin chapter 8 here. Okay, so in chapter 8, we're going to continue with what we learned in quantum mechanics and apply them to the trends in the periodic table. And by the end of this, of this lecture, we will see that we can expand what we have learned here to electron configurations. What they tell us about the arrangement of the electrons in each of the atoms of the elements. Okay, so the first topic we'll talk about is ionization energy. So ionization energy answers this question: what if the electron and the hydrogen gained enough energy to break free from the attractive force from the nucleus? Okay, so when an atom loses an electron and is free from the influence of the nucleus, we call this the ionization energy. And we can represent this as any element in the gas phase. When we irradiate it with light of enough energy, we can generate a gaseous ion in the gas phase and get a free electron, which we can detect using a detector. Okay. So the quantity of this energy, we call it the first ionization energy. So usually this is the energy needed to remove the electron from the lowest energy state of a neutral hydrogen atom in the gas phase to form, a positive ion. Okay, so we'll talk about another trend that's kind of the opposite or the reverse of ionization energy, or the energy associated when an atom gains an electron. So they're closely related. Okay. So just a little background here. It takes 1,312 kilojoules per mole of energy to remove electrons from 1 mole of hydrogen atoms. So in some context, that's enough energy to raise the temperature of 4 liters of water by more than 75 degrees Celsius. So that's a lot of energy. So it tells us that these electrons, they're bound. They don't want to be lost, generally speaking, because you generate an unstable ion in the process. So these are high energy species. Okay. So for the ionization energies of all the other atoms, we measure it by determining the radiation. The smallest amount of energy possible needed to remove, just one electron from an atom. And it turns out most of the time, the electron that is removed is the outermost or the most loosely held electrons, or in other words, the valence electron, one of the electrons in the valence shell. Okay. So if we recall the photoelectric effect, we saw this, that you shine enough light on an element, the electrons will be ejected from a metal surface, and it shows us that the electrons, they can absorb light in specific wavelengths or in specific energy values. So it tells us that light there's a particle nature of light as well. So light comes in forms of packets called quanta. Okay, so here are the ionization energies of the first 12 elements. And you see there's a generic trend here as we go across the periodic table. So let's see, going across the periodic table here, we go across the periodic table, we will see that it will go here. So we go across the periodic table, right here, going down from 1 to 2, so that's across the periodic table. And then when we go to lithium, this is the start of the n equals 2 level. And then when we go all the way down to now sodium, that's n equals 3 level. And you see here the ionization energies, as you go across the row to 1 to 2, it increases, it generally increases. And then when we go from lithium to neon, it generally increases, but there's a little bit of a gap here, going from beryllium to boron. Okay, but you see here as as we keep going forward, there is generally an increase, but there's also a gap right here for oxygen. And then, generally speaking, if we go down all the way to neon, it generally increases. So there are some exceptions here, and it has to do with, I think it has to do with putting electrons in a new orbital. Like for boron, you're putting it in a p orbital, so since it's in the p orbital, it generally decreases because p orbitals are further away from the nucleus than an s orbital, so it's going to be held less tightly from the protons. And then here we see that when we go to a new group down a period, it decreases dramatically here. But if we think about if we're going from boron to oxygen or nitrogen to oxygen, there's a decrease in the ionization energy, because if you think about nitrogen's 2p electrons, it has a filled p shell, a half-filled p shell. But oxygen, when we get additional electron there, because oxygen has 6 electrons and 4 of them are in the p orbitals. When we pair up the last electron, it's going to go into an already filled orbital, and that will have electron repulsion, and that will cause the electron to be held less tightly because of the repulsive force acting against the attractive force. So it'll disrupt the attractive force of the electron, so it won't be able to be held as tightly. So that's why we see an exception there. So generally speaking, ionization energy increases, so it increases across a row. Okay, so when we go left to right, so across the row from left to right, okay, and then when we go down a period, so down a group, it decreases. It generally decreases. So we're going from n equals 1 level to n equals 2. We see that it drops dramatically to 520 from hydrogen to lithium. Then we go from sodium, it drops even more to 495.8. And then as we go across the row from the n equals 3 level, from sodium to argon, we see it generally increases here. And then we see some gaps here, right? And that's because we're changing into a different sublevel. And then when we go into across the P block, aluminum to silicon to phosphorus, and then just like what we saw with oxygen, sulfur experiences a minor decrease in energy. And that's because of pairing up an already filled electron shell, p orbital. Okay, and then generally it increases here until you get to argon. Then we go to sodium, potassium, where the n equals 4 level begins, and we see that trend there. Okay, and we can kind of see these trends here. So these gaps here represent new energy levels. So this will be n equals 1, n equals 2, n equals 3, then n equals 4. Like so. Okay? So generally speaking, ionization energy increases. So why does it increase as we go, as we increase the atomic number? It's probably it's because the atomic number is increasing. And so what that means is the nucleus is getting more protons in it. So when it has more protons, has a higher nuclear charge, and then electrons will feel a greater pull of attraction from the nuclear charge, so it'll be held on more tightly. So that's why electrons across the row, it generally increase their ionization energy, because it takes more energy to remove a valence electron from an increasing nuclear charge. And then as we go down a period or down a group, ionization energy generally decreases, because as electrons are added, as valence electrons are added to the atoms, the valence shell is going to get further away from the nucleus because you're entering new principal energy levels, and that's going to be increasingly away from the nucleus. So it's going to be held less tightly, because remember Coulomb's law, the force of attraction between two particles, it dies it decreases very quickly with the square of the distance. So the further you're away from the nucleus, the less of an effect you will feel for attraction to the nucleus due to nuclear charge. So that's why we see those trends there. Okay. All right. Which would you expect to be larger? The first ionization energy of rubidium or strontium? Okay. So let's look at our periodic table. So I would generally do this in class so we could look at the periodic table together. But we can't do that now. But I'll pull up. So I recommend students when they answer these questions, get your periodic tables out, and then we'll discuss as a class right here. Okay, so I'll pull up a periodic table. I expect students to do the same while doing these lectures as well for certain problems. Okay. So if we look at strontium, it's in group 2. Okay, and rubidium is in group 1. So we look at a periodic table. Rubidium is in group 1. So we have group 1, and then we have n equals 5. Okay, it's in the 5th energy level. And then strontium is in group 2, the same energy level, n equals 5. Okay. So they're in the same energy level, but they're in different groups. But so they're right next to each other. Okay. So when they're right next to each other, remember when we increase from left to right, we're going to see an increase in ionization energy. So we would expect the first ionization energy of strontium would be greater of strontium. Whoops, no, of rubidium. So for these types of questions, especially on exams, we should really practice on writing complete, concise, and succinct explanations to questions. Those will be the best. So it's way better than using a wordy way to phrase things. So if students are having if you're finding it difficult to explain things, I would try to do your best at explaining out loud, and maybe record yourself and see how you sound, and maybe try to reduce it into like more simpler terms, or try to shorten it the best you can so it's easier to remember. So these explanations are easiest to remember if you kind of say over a lot to yourself over again. That's what I did when I first learned this in high school. Because in high school, my teacher wasn't very good for AP Chem, so I kind of had to teach that myself. So, but it was fun. I mean, I kind of learned more that way, in a sense. But my recommendation is if the concept's confusing, get some help, or kind of think about an explanation that makes sense to you, and that kind of makes sense of what is correct. And then if you can do that, it won't feel like you're memorizing anything at all. Okay? All right. So we said the first ionization energy of strontium would be greater than that of rubidium. And that's because strontium has one more proton in its nucleus. Then rubidium And therefore, attracts its electrons more strongly than does rubidium. So that's what we would expect. But I don't think we have a value for it. Well, actually, there is a value for. Let's just check the values right here. Okay. So rubidium is. Let's see here. 37, and then strontium's 38. So yeah, the trend is pretty much that strontium has a stronger ionization energy. So we usually see these dips in the trend. You see here, you really only see these dips here between the change in sublevel, and then when you start pairing up electrons in the p shell. You don't really see this when you're going from the lithium to beryllium, sodium, magnesium, and potassium to calcium. And again, we don't see this. We don't see a deviation from the trend going from rubidium or strontium, and that's because s orbitals tend to be closer to the nucleus, so they're more attracted to the nucleus. So pairing up electrons in an orbital doesn't really have a great effect when it's in an s orbital, and that's because the spherical orbitals, they're kind of situated closer to the nucleus. Okay. So I would say these types of questions will require, some deep thinking. There's not really a lot of math involved, so we'll have to kind of rationalize things based on a little bit of physics, and a little bit of the attractive forces present in our world. Okay, let's do the second question now. Which would you expect to be larger, the first ionization of chlorine or bromine? So let's explain. So chlorine is in group 7 as well as bromine, but chlorine is in the 3rd principal energy level, and bromine's in the 4th principal energy level, directly below chlorine in the periodic table. So now we're considering elements that are in 2 different energy levels. Okay. The first ionization energy So when you're answering these types of questions and it tells you to explain why, so think about an explanation that you think will be that will answer the question completely. So usually when you have an explain why question, you have to write a little bit more than one sentence. Well, it really depends on the type of question being asked, but usually I expect a few sentences, 2 to 3 sentences for explanations, and usually that does it. That usually answers the question completely. Okay, the first ionization energy of chlorine, okay, is greater. So we know bromine is lower than the periodic table, right? Than chlorine. So that tells us the electrons are further away from the nucleus. If that's the case, it's going to be held less tightly, and then the energy required to remove that electron is going to be less because there's a less force of attraction for the electrons in bromine than chlorine. So, in my experience, students try to find ways to shorten explanations into like a few words, but unfortunately, sometimes that's not possible. So, I would really encourage students to kind of paraphrase things I say that make sense to them without losing any general meaning of the phrase of what I tell them. So, it's easy to like just kind of paraphrase things and kind of memorize them, but gotta remember, if it doesn't make sense to you, you won't really remember it all that well. So I recommend that students try to make sense of the solutions I provide and by paraphrasing them. Okay? All right, so let's stop here, and then when we come back, we'll talk about the shell model of the atom. Okay, so I'll see everyone in the next video.